Hello, my darlings. So we are going to talk about 3A notes, which is our exponential functions. We have finally finished Unit 7, which was rationals, and so this is the beginning of Unit 8. This is our last unit for the year, which is exponential and logarithmic functions. So obviously we'll start this week with exponentials. Next week we'll still be talking about exponentials, and then we'll get into our logarithmic functions. So an exponential function is, the parent function looks like y equals b to the x power, or y equals a times b to the x power. So if you notice, your variable x is the exponent, hence exponential functions. So we are going to be looking at b is what is known as our base, okay? If that b value is greater than 1, this is going to be showing a growth. Well, what does that mean? Well, if b is bigger than 1, let's say b is 2. If I have 2 to the x power and I start plugging in x's, let's see what we get. 0, 1, 2, I could do negative, I could do, whatever. So 2 raised to the 0 power. Anything raised to the 0 power will always give us 1. So if that base would have been 3 or 4 or 10 or 100, anything raised to the 0 power has a value of 1. So that means when x is 0, no matter what our base is, the value of that exponential function will be 1. So on any single exponential function that hasn't been transformed, there will be a point 0, 1. Okay, now let's continue with this base of 2. If x is 1, well, 2 to the first power is just 2. Well, what about 2 squared? That would be 4. What happens if I have a negative exponent? Let's remember our exponent rules. If I have a negative exponent, that's the same thing as writing the reciprocal. So 2 to the negative 1 power is really 1 over 2 to the first power, which is just 1 over 2. 2 to the negative 2 power is the same thing as 1 over 2 to the second power, which is 1 over 2 squared, which is 1 over 4. So if we were to plot these points, I know I have that point 0, 1. Then if x is 1, y was 2. If x was 2, y was 4. And then on this left-hand side, negative would be a half. Negative 2 would be a fourth. Negative 3 would be an eighth. Yada, yada, yada. So on and so forth. I'm hoping you notice that will you ever get a value that is negative for an exponential function? No matter what kind of x value you plug in, you will never get a y value that is negative. 2 to the any power you can think of will never be a negative number. So we have that horizontal asymptote, remember, horizontal asymptote is going to be at y equals 0 here. It's going to get closer and closer and closer to 0 on the left-hand side, but it's never going to touch or cross that value. Now, every time we introduce a new parent function, we'll talk about transforming that parent function, which we'll do on Thursday's lesson. 3B's lesson is transforming these exponentials. So if we have some kind of flip or stretch or shift, obviously this is going to change. But for the parent function, you're never going to have a negative value. You're always going to be crossing through at that point 0, 1. Okay, so this is what's showing a growth exponential function. That's when our b, that base, was bigger than 1. Well, what if that b value is not bigger than 1? What if it's between 0 and 1, right? That's going to be showing decay. Okay, we have growth and we have decay. So if that b value is between 0 and 1, it's going to be showing decay. Well, let's say we pick 1/2. Okay, let's say b is 1/2. So now we have x, and then we have 1/2 to the x power. Again, let's do our -2, -1, 0, 1, and 2. I'll start at 0 because we know anything raised to the 0 power is going to be 1. So that 0.01 is still there, even though we know that this is going to be showing a decay and not a growth, okay? 0.01 will still be there. If I raise it to the first power, 1/2 raised to the first power is just 1/2. If I raise it to the second power, remember if I raise a fraction to a power, it's really like raising the numerator to that power and raising the denominator to that power. So 1/2 squared is really 1 squared over 2 squared, which is 1 over 4. Now, if I go to those negative exponents, it's still applying that same property that we're taking like the reciprocal of it. So if I have 1/2 raised to the negative 1 power, I'll just write it down here, 1/2 raised to the negative 1 power, that's really the same thing as 2/1 to the first power. Well, that's just going to be 2. If I have 1/2 to the negative 2 power, well, that's the same thing as 2/1 to the second power, which we know is 4. So if I had to plot these points now, -2, 4 would be somewhere up here. -1, 2 would be somewhere here. +1, 1/2. +2, 1/4. Notice this is now showing a decay. Still having that horizontal asymptote at y = 0. Okay, it's going to get closer and closer and closer to 0. If this was a 3, that would be a 1/8. On and on and on and on and on. It's going to get closer and closer to 0, but it will never equal 0, and it will never equal a negative value for these parent functions. So b is at base. So if it's greater than 1, it's going to be showing a growth. So it's going up from left to right. If b, that base, is a number between 0 and 1, then it's going to be showing a decay. It's going down from left to right. Now, what if, maybe you're thinking, well, what if b is a negative number? Can b, our base, be a negative number? Well, let's think about what that would look like. Let's say I choose -2, and I'm using 2 and 1/2 just because they're easier numbers to work with. You could choose 5 or 10 or 3 or whatever. Let's say I choose a negative base. So let's say we have, -2 to the x power. X -2 to the x power. Let's see what happens. -2, -1, 0, 1, 2. We know that anything raised to the 0 power will be 1. That's an easy one. Well, -2 to the first power is -2. But -2 squared is a +4. -1 as an exponent. -2 raised to the -1 power would be -1/2. But -2 raised to the -2 power would be a +1/4. This creates an issue for us because we have positive to negative to positive to negative to positive to negative. Lots of jumping up and down here, okay? Also, we would create a lot of holes in these graphs depending on what your base value is. So we are not going to be doing any negative bases. Now, I want you to keep in mind that something that looks like this -2 raised to the x power, is going to be different than something that looks like this. Why? Think about your transformations. We're going to talk about that on Thursday, but think about that. This is showing a reflection over that x-axis, okay? This is being reflected over the x-axis. It has a base of 2 raised to the x power. That is different than -2 raised to the x power. So just something to kind of stick in your head and think about for the rest of this week. Also want to make mention of one more thing before I move on to the next section, is this part right here where it says A is our initial amount or our initial value. Okay, if I give you something like 2 times 3 to the x power, that is not going to be the same thing as 6 to the x power. In this equation right here, 2 is our initial amount, so it's going to be acting as that vertical stretch in terms of transformations. 3 is our base, and that's being raised to the x power, okay? Okay, so all we want to decide here is whether these exponential functions are showing growth or decay. So remember, if that b value, if that base is bigger than 1, it's going to be showing growth. It's going to be going up from left to right. If that b value is between 0 and 1, remember it's not going to be a negative number, but if it's a number between 0 and 1, then it's going to be showing decay, going down from left to right. So in part A, our base is 3. 3 is bigger than 1, therefore this is going to show growth. Okay, now to graph that, I want to label 3 points. The easiest points to pick for these growth and decay problems are using an x value of -1, 0, and 1. 0, as you've heard me say a couple times already, an x value of 0 will always give you a y value of 1 unless it's been transformed. Okay, so if I were to plug in x 3 to the x. Negative 1, 0, and 1. So if I plug in negative 1, I'm going to get a 1/3. If I plug in 0, I get 1. If I plug in 1, I get 3. And I can easily plot those points, even though I know that I'm estimating here 0, 1, 1, 3, and then negative 1, 1/3. And there's my growth. Okay, for the second problem, I have a base of 3/4. Well, 3/4 is a number between 0 and 1, therefore, this is going to show decay. Okay, I want to plot this, so I'll make myself a little chart. Now I have 3/4 raised to the x power. Again, I'll choose negative 1, 0, and 1. I know that anything raised to the 0 power is 1. I know that anything raised to the first power is just itself. And then if I raise that to the negative 1 power, that is going to reciprocate that fraction. So that's actually going to give me 4/3, which is a little bit bigger than 1. So if I plot these points, 0, 1, 1 3/4, and then negative 1 4/3, I see that decay. All right, next up, I have 2 times 3/4 to the x power. So notice this one has that a value, okay? The base is still what's going to tell me if it's growth or decay. My base is still a number between 0 and 1, so this is going to show decay. Even though it has an initial value of 2, which is bigger than 1, that doesn't affect the shape of the graph, okay? That's just, think about that as your vertical stretch, okay? It doesn't change the shape, it just stretches it. So again, I'll make myself a little table, 2 to the 3/4 to the x power. I'll still choose these 3 points just because they're the easiest x values to plug in. Now this time, following the order of operations, 3/4 to the 0 power is 1, but 1 times 2 is 2. So now I don't have the point 0, 1 because it's been transformed. It has that vertical stretch now. It has that initial value. So instead of 0, 1, I have 0, 2. Okay, when I plug in 1, 3/4 to the 1 power is 3/4 times 2 is going to give me 6/4, which can be reduced to 3/2. And then negative 1 is the x value. 3/4 to the negative 1 power would give me 4/3. And then times that 2, that initial value, is going to give me 8/3. Okay, so plotting these points, 1, 3/2, and then negative 1, 8/3 would be up here. So again, still showing that decay. And then our last problem here, we have y equals 5/4 to the x power. Be careful. Just because it's a fraction doesn't mean that it's between 0 and 1. 5/4 is a number that is bigger than 1, so this is going to show growth. Okay, make myself a little chart. 5/4 to the x power. Going to pick those 3 same x values that I have been doing. This is going to give me 1. This is going to give me 5/4, and then this is going to give me 4/5. And so when I plot those points, I'm estimating here, but you should understand the pattern now. Okay? In this unit, we're going to be using a number that's called Eulers number. It's actually pronounced Euler, not Euler. And that's E. It's a lowercase e. You can find it on your calculator. I don't remember where it is on the Casio, but if you're using like a TI, I know it's on the left-hand column. It's going to be one of those things in the offset color. You have to press like shift or something, but it is on your calculator, lowercase e. And this is an irrational number. This is not a variable. This is actually a number, and it's extremely similar to pi. Pi is that irrational number that we use all the time in geometry and in math. E is going to be a number that you're going to be using a lot in this unit and a lot in pre-cal and calculus. Okay, so I'm just going to show you kind of a couple ways on how to estimate that number. Obviously, we cannot be exact because it is an irrational number, so it goes on forever and ever and ever and ever and ever, just like pi does. Okay, but one way to estimate it is to use this formula, 1 plus 1/x, all of that raised to the x power. So as x approaches infinity, we will get closer and closer and closer to that value of e. So I just broke down a little table here using 10 and then 10 to the second power, which we know is 100, and then 10 to the third power, which we know is 1,000, and then 10,000, and then all, et cetera, et cetera, et cetera. So this is something that you will definitely need your calculator for if you're going to estimate along with me, and anytime that you're going to be using E in a function or an equation when solving, you're going to have to use a calculator, just like we do for pi. Okay, so if I plug in just 10, so that would be 1 plus 1 over 10, all of that raised to the 10th power, I get something like 2.5937. And I'm going to jot down a couple decimal places just to show you the small change over time and how it gets closer and closer and closer to a specific number. Okay, then I'm going to plug in 100 for x, 10 squared. So if I plug in 100, 1 plus 1 over 100 raised to the 100th power, I get 2.7048. Now I plug in 1,000, which is 10 to the third power. I plug that in, 1 plus 1 over 1,000 raised to the 1,000th power. I get 2.7169. I keep going on and on and on. I get 2.71815. I get 2.71827. I get 2.71828. And you can pause the video right here and plug these numbers in to see exactly how I'm getting them. But this is the closer and closer and closer you get to infinity. Think about how large 10 to the 6th power is. That's 6 zeros, okay? You get closer and closer and closer to infinity with your x value, but look at what's happening to this number. It's getting closer and closer and closer to one value. Obviously, all of them are starting with a whole number of 2. So it's approximately 2 point. Well, it first started out with a 0.5, but then it was a 0.7, 0.7, 0.7, 0.7. So it's definitely getting to 0.7. Then we see that it was approaching 2.71. Then we noticed it was approaching 2.718. Then we noticed it was approaching 2.7182, etc., etc., etc. I'll go ahead and stop here. You don't have to write all these digits down, obviously, but 2.718. That is what we use to approximate E. Just like pi, we normally approximate it as like 3.14 or 3.159 or whatever. E is approximately 2.718. Something that is unique about this function of y equals e to the x power. Remember, e is not a variable. E is a number. So this is really the same thing as saying y is equal to 2.718 raised to the x power. Interesting thing about that, obviously you know that this would be showing growth because e is a number that is bigger than 1. So this is going to be showing growth, and I'll just kind of make a sketch of that. Okay, it says that the slope at a point on the graph is the same as its value of the function. What does that mean? If I were to pick any point on this graph, let's start with an easy one. This would be 0, 2.718. That is 0, e. They're talking about the slope at the point on that graph. So if I were to draw a tangent line at that point on the graph, the slope of that blue line is e. It is the value of the function. If I were to pick any other point on that graph, let's say I was all the way up here. If I drew a tangent line, that would be, let's say that this is an x value of 2. So that would be y equals e to the second power. That number, because that is a number, is the same thing as the slope here. Okay, this is going to be really important in calculus. Like I said, e is used a lot, obviously, in this unit, but in pre-cal and calculus. And the reason being is because calculus is all about derivatives. Derivative is the slope of that tangent line on the graph. Okay, so just something interesting to you. Here, hopefully these will make you feel really good because we're just simplifying the expression. Okay, so this is just really practicing and reviewing your exponent properties and rules, which is what we did back in Unit 6 with radicals and rationals and way back in the days. Feels like so long ago, but remember, e is a number. So it says we have e to the third power times e to the seventh power. Well, if I multiply the same base, what do I do with the exponents? I add the exponents. So this is going to be e to the 10th power. Done. Going on to b. Notice I'm dividing. So I'm going to divide all my numbers, and then with the e's, because they're the same base, what can I do with those exponents? I subtract them. So what is 25 divided by 5? 5. What is e to the 13th power divided by e to the 12th power? E to the first power. You don't have to write that exponent of 1, as is always understood. So that would just be 5e. Okay. Then we have y equals 2e to the negative 3x power, all of that raised to the 5th power. Well, what happens when you raise a power to a power? You multiply. So everything in that parentheses gets raised to the 5th power. Well, we have 2 to the 5th power then, and then we have e to the negative 15x power. Remember, I multiplied, so negative 3x times 5 is negative 15x. This is not my final answer because I can simplify it a little bit further. We know that 2 to the 5th power is 32. E to the negative 15x power. What happens when you have a negative exponent? Remember, it gets reciprocated. So this is now going in the denominator. I cannot simplify any further. Therefore, that is my final answer. Pretty easy. So here we're just talking about, again, growth and decay. So earlier in the notes, we said that when the exponential function is showing growth, that base value needs to be greater than 1. And for it to show decay, that base value needs to be between 0 and 1. Well, if we're talking about e in our function, e as our base, e is always going to be a number that's bigger than 1. But we can still use e in the function and show decay. So here we have e to the x power. Well, we know that's going to be a growth function, so all those properties are going to be entailed here. We have that horizontal asymptote at y equals 0. We're showing growth, so we are still going through the point 0, 1, 1, e, right? E to the first power would be e, which is that 2.718. And then if we have negative 1, that would be 1 over e, or 1 over 2.718, which is what I sketched on the graph there. Done. But how do we show decay with a base of e? Notice in the second graph, we have y equals e to the negative x power. Think about this as a transformation. When we have a negative with the x in our transformed function, that shows a reflection over the y-axis. So if I take this e to the x and I reflect it over the y-axis, now that's going to look like decay. Still having that horizontal asymptote at y equals 0. You can still plug in some numbers here. 0, 1, negative 1. Well, if I plug in 0 for x, that's still 1. That's still e to the 0 power. Negative 0 is the same thing as 0, right? So we still get 0, 1. If I plug in a positive 1 there, then that's really e to the negative 1 power, which is 1 over e, which is here, that fraction. If I plug in a negative 1, well, a negative of a negative 1 is a positive 1, so that's actually going to give me that positive e value, which is somewhere up here. So that's showing decay. So when e is your base, you have to look at the exponent to decide if it's going to be growth or decay. A positive exponent will be growth, and a negative exponent will show decay. Okay, so let's just review that property. Determine if the function represents growth or decay. So notice in A, B, and C, the base of those exponential functions are all e. E is that number that is approximately 2.718, so obviously it's bigger than 1. So we have to look at the exponent to see if it's showing growth or decay. So in the first problem, we have e to the negative 4x power. That has a negative exponent. That means it is showing decay. In part B, the base is e, not 0.3e. Remember, 0.3 is just like that transformation of a vertical stretch or compression. That's just the initial value. It does not affect your base. Your base is still e. What is the exponent? 5x. Because that's positive, it is showing growth. And then in part C, again, our base is e. So we look at our exponent. Because the exponent is negative, it's showing decay. So the last thing we're going to do on our notes today is we're going to rewrite our exponent function into a different format, which is going to help us decide the exponential growth or decay rate. And that's going to be really helpful and beneficial to us at the end of this week and next week when we talk about real life applications. Where do exponential functions show up in our everyday lives? You've probably heard this word exponential growth if you've been watching all of our news, the media about this COVID-19. It is growing exponentially. So this is something that is actually very beneficial to us right now in our everyday life. What is that growth rate? We can actually figure that out. So I'm going to show you how to rewrite something in the form of this y equals ab to the x power into something that will show us easier what that growth or decay rate is. So the first thing we need to talk about is we need to review those exponent properties. So we have y equals 2 to the 2x power, and we need to rewrite that in the form of a, some initial value, times b to the x power. Well, let's think about those exponent rules. If I have a power raised to a power, what do? I multiply them together. 2 and x are being multiplied in that exponent. So that's the same thing as me saying y equals 2 squared to the x power. If I gave you that problem, you're raising a power to a power, you would have multiplied them and you would say that's 2 to the 2x power. So we have written the same exact thing down. Well, now we can just simplify this a little bit more. You know that 2 to the second power, 2 squared, is 4. So this is really just y equals 4 to the x power. And that's all I needed to know. So we're going to take this concept and apply it to some different functions to see that growth or decay rate. Okay, so here we're going to still apply those exponent properties. We're going to rewrite our function into the form of y equals a times either a plus r or a minus r raised to the x power. Remember, if it's a plus r, so if it's 1 plus r, that means it's 1 plus some number. That's going to be a number bigger than 1. Therefore, this is going to be showing growth. Okay, because remember, if our b value is bigger than 1, that's showing growth. If it's 1 minus r, so 1 minus some number, that's going to be a number less than 1 but bigger than 0, so that's going to be showing decay. Remember, if that b value is less than 1 but bigger than 0, it's showing decay. So you can think of this 1 plus or minus r equaling that base, equaling your b value in that y equals ab to the x power. So first thing I want to do is I want to rewrite. So I have y equals a times. Well, instead of 2 to the x divided by 3 power, I know that's the same thing as 2 to the 1/3 power raised to the x. Why do I know that? Because a power to a power, I multiply. If I have x over 3, that's the same thing as 1/3 x, which is the same thing as the base, which is 2 in this problem, raised to the 1/3 raised to the x power. So I have not changed anything. I am just rewriting. Everything is equal. Now at this point, you're going to have to grab a calculator. So if you don't have a calculator at home, you can use the one that I've posted on Schoology, that VM through the Horizon app on your iPad, or you can use Desmos or any kind of internet calculator that you can find. It doesn't have to be a fancy one. If you just have like a normal calculator at home, that'll totally work. You could probably even use your iPhone, honestly, because all we're going to be doing here is evaluating 2 to the 1/3. So I'm literally just typing in 2 raised to the 1/3 power, hitting enter. I get a decimal, and that decimal is going to be about 1.26. So again, I've just rewritten this. I haven't changed anything. I haven't done any math. I haven't solved for anything. I'm just rewriting. Okay. Now Now it's kind of looking more like that y equals ab to the x power. Our b is 1.26. Well, that's a number bigger than 1. So this is showing growth. So because this is showing growth, I want to rewrite it as this 1 plus r as my base. Well, if I have 1 plus 2, 6, then I know that that is 1 plus 0.26 raised to the x power. Why is this beneficial to us? This is beneficial to us because now we can see not only do we know that this is growing exponentially, but we can point out very quickly what that percentage rate is. That R stands for rate, and we always write our rate as a percent. So 0.26 is 26% growth rate. So whether we're talking about money in the bank or this COVID spread or whatever, it is exponentially growing at a 26% rate. Remember, when I give you a decimal, you move that decimal 2 places to the right, and that will give you your percent. For the second problem, we're going to do the same thing. So first thing I want to do is I want to rewrite. So this is the same thing as y equals a times 0.5 to the 1/12 power raised to the x. I have x over 12. That's the same thing as 1 over 12 times x. So it's 0.5 raised to the 1/12 power. Again, you plug that into your calculator, you get a number, and that number is about 0.944 raised to the x power. At this point, I need to determine, is that growth or is that decay? Well, 0.944 is a number that is less than 1 but bigger than 0. So this is showing decay. It's a number less than 1. So I know that I need to use the formula of a times 1 minus r. Well, 1 minus r has to equal that 0.944. So I need to find like its complement. 1 minus what number? Well, that's going to be 1 minus 0.056. That's what gave me 0.944. And at this point, remember, this decimal right here is showing me the percent of that decay. Move that decimal 2 places to the right, and we get a 5.6 decay rate. Okay, in our last example, we're going to do the same process, but the only difference here is that our base is e. Okay, so remember, you can immediately determine if it's going to show growth or decay looking at the exponent. Positive exponent with a base of e is growth, negative exponent with a base of e is going to be decay, but that's not enough for us. We want to know that rate. We want to rewrite it in that form of either a times 1 plus r to the x power or a 1 minus r to the x power. So first thing I want to do is rewrite. So now I have y equals e to the negative 0.5 raised to the x power. Okay, at this point, I plug this into my calculator. Remember, e is a number. If you're using the Casio, the e is going to be in that offset color above your LN button, which is kind of in the middle towards the top. LN is natural log, e is right above it. You'll see e to the x power, so you'll have to hit shift and then that LN button and you'll pop up e to the whatever power, and that's a negative 0.5 power. Or if you're not using a Casio or a TI or something like that, try to just plug in that estimated value of e. You'll have some round off error, but at least you'll get the idea of how to do this. So I'm plugging in e to the negative 0.5 power, and that's going to give me a big old decimal, and I'll just write these 3 decimal places, 0.607. Okay, I would always say between 2 to 3 to 4 decimal places is good, not just 1. 2 if, but 3 is good. So again, at this point, I know it's going to be a decay because now my base is a number less than 1. I knew it was a decay to begin with because it had a negative exponent, but this just proves to me. So I need to rewrite that in the form of 1 minus r. So this is going to be y equals 1 minus, the complement of that is 0.393 raised to the x power. So again, I know it's decaying, but now I can give the exact rate at that it's decaying, which is going to be 39.3%. Remember, I take that decimal, move it 2 places to the right, and that gives me the 39.3% decay rate. Again, first step, rewrite. So we have y equals 0.5, that's just our initial value, and that's going to be multiplied by e to the 0.8 power raised to the x. E is our base, it's a number bigger than 1, so I have to look at the exponent. Because it's positive, I know that this is going to be a growth, but I still need to rewrite it so I can get that rate. So at this point, I need to simplify. I plug in e to the 0.8 power in my calculator, and that gives me a decimal of 2.226. Because I know that this is a number bigger than 1, it's showing growth, I want to rewrite it using that form of 1 plus r. Remember, 1 plus r is for growth, 1 minus r is for decay. So rewriting this, I get 0.5, which is our initial amount or our initial value. 2.226 is going to be 1 plus 1.226. This means that my growth rate as a percent is 122.6%. I move that decimal 2 places to the right, and that means it's getting bigger more than its initial amount every single year or day or hour or whatever your x value is in terms of. And there you go.